Tonight, I want to tell you a story about learning, but not the kind you do with flashcards or lectures. A quieter kind, one that happens bit by bit, often in silence. I want to talk about how machines learn by taking tiny, thoughtful steps. Downhill. This is the story of gradient descent. It sounds technical, and it is. But beneath the surface, it's a gentle idea. One that mirrors the way we too find our way forward when the world feels uncertain. So settle in, let your mind soften, and sleep on this. Imagine standing on a foggy hillside. You can't see far ahead, but you want to find the lowest point. How do you do it? You take a step. Then you ask, is it lower here than before? You keep stepping gently, each time choosing the direction that seems to slope downward. This is gradient descent. It's not a sprint, it's not a leap. It's a walk. A soft, cautious walk in the direction of improvement. A process of sensing, correcting, and stepping. Again and again. Now, let's imagine that hill is a problem, and you want to solve it. You start with a guess. The machine doesn't know what the answer is, so it makes a guess. Maybe it's wildly wrong, but that's okay. Because after that guess, it gets feedback. A signal, telling it how wrong it was. This feedback is a number, a single value called a loss. It tells the model, here's how far off you were. And now it asks the key question, how do I adjust to be a little less wrong? It looks at the slope, the gradient. It finds the direction where the loss decreases most quickly, and it steps. Just a little. That step is calculated. Using calculus, yes, but in spirit, it's intuitive. It's like putting your hand out in the dark, feeling which way the floor tilts, and deciding to lean that way. Each weight in the model adjusts by a small amount, not all at once, but with care. Too big a step, and you might overshoot. Too small, and learning takes forever. So machines learn to balance. They find a pace that suits them. This pace is controlled by something called the learning rate. A simple number that tells the model how big its steps should be. Too high, and the model might stumble. Too low, and it might take forever to reach the bottom. Learning rate is a kind of trust. How much the model believes its current feedback, how boldly it follows the slope. But what is a slope mathematically? It's a measure of change, of how steep the loss function is at a point, of how sensitive the error is to each weight in the model. If the slope is steep, a small change in a weight makes a big difference. If the slope is flat, the weight barely affects the output. The gradient is a vector of all these slopes, one for each weight. It points in the direction that increases error the most. So to reduce the error, we go the opposite way. We step against the gradient. That's why it's called descent. We're stepping down toward lower loss. Picture a map made of air pressure. You see the lines, tightly wound in some areas, wider apart in others. The closer the lines, the steeper the slope. Now imagine the model walking through this map, feeling how steep the land beneath it is without seeing it. It leans gently. It tilts in the direction of decreasing pressure. This invisible landscape is the loss surface, and gradient descent is how the model learns to navigate it. Now imagine we have thousands, maybe millions of weights. Each one is part of the model. Each one changes the output. Each weight has a slope. Each slope forms part of the gradient. And the model steps, not blindly, but following this high-dimensional direction. It doesn't just change one weight at a time, it changes all of them together. A soft choreography of parameters adjusting themselves. A quiet harmony of little shifts in response to error. Let's ground this with an example. Imagine a model trying to learn to predict house prices. It gets data, number of bedrooms, square footage, location, and it makes a prediction. $340,000. The real price, $390,000. There's a gap, an error, and that error feeds back. The model sees that when square footage is large, its estimate is too low. So maybe it should increase the weight on that feature. And it does. A little. Maybe it overcorrects, or maybe not enough. Either way, it learns. Each example it sees is like another part of the hill, another step down, another bit of the shape of the lost landscape. Let's imagine a different example. Suppose you're adjusting a recipe. Your cookies come out too dry. So you add a little more butter. Still too dry? You add a bit more. Now they're perfect. That's gradient descent, a small adjustment based on the outcome. If you overdo it, too much butter, you notice and dial it back. Eventually, you learn the sweet spot. This is how models learn too. Each time they predict and receive feedback, it's like tasting the results and refining the recipe. This landscape can be strange, twisting, curved, riddled with valleys and peaks. Sometimes the model gets stuck. It finds a low point, but not the lowest. We call these local minima. They're like comfortable mistakes. Places where the model feels it has improved, but hasn't found the best it could do. There are techniques to escape them. Adding momentum, restarting from new places, using noise. These help the model keep moving, to not settle too soon. Momentum is an idea borrowed from physics. Imagine pushing a sled down a hill. If you only nudge it gently, it might stop in a dip. But if it's moving fast enough, it might roll past that dip and continue down. In optimization, momentum helps the model keep moving in promising directions even if the local terrain is a little bumpy. It smooths the ride. Think of this like life. We too sometimes stop short. Think we've figured something out, only to later realize we were stuck. We were in a dip, but not a valley. We were still far from understanding. Gradient descent reflects this. This learning is not instant, not linear. It's a practice of gentle adjustment, of staying with feedback, of listening. and stepping. Let's go deeper. What guides the entire learning process is something called the loss function. It's the machine's measure of how far off it is from the desired outcome. It might be as simple as the difference between the predicted and actual number, or it might be more complex, a function that penalizes some errors more than others. There are many types of loss. Mean squared error, which punishes big mistakes more than small ones. Cross-entropy loss, common in classification problems. Each one shapes the surface the model walks on. Choosing the right loss function is like choosing the right lens. It determines what matters most to the learner. If you measure badly, you learn badly. Now enter the optimizer, the brain of the walk. It takes the gradient, that slope of error, and decides how to move. There are many optimizers, but most are built on gradient descent. Some use momentum, remembering past directions and speeding up when paths align. Some adapt, changing the learning rate depending on how noisy or stable the terrain becomes. Adam is one of the most popular. It combines ideas of momentum and scaling. It listens not just to the current step, but the recent history. Like a hiker who has walked this way before and knows when to slow down and when to keep going. The model doesn't usually learn from all data at once. That would be slow, heavy. Instead, it learns in batches, small portions of data, randomly selected. Each batch is like a snapshot of the whole landscape. The model steps based on that, and then takes another step on a new view. This creates randomness, noise, but noise too is useful. It keeps the model from memorizing the hills it's seen. It makes it generalize, to see the broader shape, not just the small dip it stood in. After a full pass through the data, we call that an epoch, and the model goes again and again, each round refining the path. Sometimes it forgets, sometimes it overcorrects, but with enough rounds, it begins to trace the true shape of the valley it's in, until it can settle and say, "This is the best I can do." Of course, it doesn't always find the absolute best, but it finds something that works, something good enough to make predictions that feel right. This is how deep learning works. It's not rules. It's not memorization. It's refinement. It's sculpting error into understanding. You can picture it like water flowing through a jagged canyon. At first, it rushes, splashes, collides with rocks, but over time, it carves out a smooth path. The river learns the shape of the earth beneath it, and the model learns the shape of the problem it's trying to solve. Not in a day, not in a rush, but slowly, through descent. In our lives, we do something similar. We make guesses, we make mistakes, we get feedback, and then we step. We try again, we tweak, we descend, and refine. Whether we're learning a skill, healing from a mistake, or navigating something new, we improve by listening to what didn't work and adjusting softly. Gradient descent isn't just a mathematical tool, it's a philosophy of learning. one rooted in humility, patience, and responsiveness. It doesn't demand perfection, it just asks, what can I change right now to move closer to the truth? And then it steps. So when you hear someone say that machines are learning, this is what they mean. Not that they're thinking like us, but that they're adjusting. Tiny steps, tiny updates. Each one a movement from error toward understanding. Each one a whisper of improvement. Let this be your rhythm tonight. Let it soothe you. That progress is not always fast. That refinement takes time. That even the most powerful systems learn gently, by stepping carefully, by listening to error, by flowing with the slope, and letting the direction reveal itself. Let your thoughts descend. Let them adjust. Let them rest. Good night. Sleep well. And sleep on this.